Question 1 from Section 2 of the 2024 Higher Physics Examination from the SQA. A Doppler ball consists of a loudspeaker and a battery-powered circuit board inside a foam ball. Two students are throwing the ball to each other. Student A throws the ball with a velocity of 11.0 meters per second at an angle of 36 degrees to the horizontal. The ball is released at a height of 1.60 meters above the ground. The ball passes over the head of student B and lands on the ground at point Q. The diagram is shown here. It's not drawn to scale, and we can ignore the effects of air resistance. 1A part I, capital A, says calculate the horizontal component of the initial velocity of the ball for 1 mark, and for part B also the vertical component of the initial velocity of the ball. It's a standard question for projectiles. There's our diagram there. You can construct it quite easily. You have the 11.0 meters per second vector like that at an angle of 36 degrees to the horizontal. And these two vectors here, the green one and the yellow one, are the components of the vector. The green one is the horizontal component, which we'll call VH, and we can work that out from our trig and just say that VH is going to equal to 11.0 times cos of 36 degrees. And we do that in a calculator. We've got the horizontal component, the size of the horizontal component vector. It turns out to be 8.90 meters per second. The vertical component of the 11.0 meters per second 36 degrees vector is found by using this formula. The vertical component is equal to 11.0 times sine of the 36 degrees angle. So we work that out in a calculator. We end up with a value of 6.50 meters per second. So there's your two components. The vertical component is going to be 6.5 meters per second, and the horizontal component is going to be 8.90 meters per second. Question 1, part A continued. The ball takes 1.53 seconds to travel from student A to point Q. Calculate the horizontal distance travelled by the ball. Well, to find the horizontal distance, we already know the horizontal speed, which is VH, and we worked that out to be the horizontal speed was going to be 8.90 meters per second. 8.90 meters per second. We know it's going to be in time of flight of 1.53 seconds, and therefore the horizontal distance travelled is just going to be equal to the horizontal velocity multiplied by the time. So we're going to have 8.90 multiplied by 1.53, and if we do that on our calculators, we end up with a value of 13.6 meters, and it's in 3 significant figures, 1, 2, 3, and that's in agreement with the amount of significant figures that we're using in the problem. Question 1A, part 3. The ball was directly above student B 0.95 seconds after it was released. Student B has a maximum reach of 2.10 meters. Determine the height h between student B and the ball, and h is shown in that diagram there. It's not drawn to scale. So for 4 marks, how do you go about doing this one? Well, the first thing we have to do is realise that everything is taken from the place of zero displacement, and that's the point where the ball is released from the person's hand. So what we have to do is, at this particular time in the flight, the ball is there. We have to work out its displacement above this centre line, and that's at a time t equal to 0.95 seconds. Now that displacement is really that height there like that. So that's what we're trying to find first of all, and therefore if we can find that height, which is the displacement at that particular point in the flight, we can add on to that 1.6 meters and we get the true height above the ground, and then we can figure out how the h can be found. So first of all, what we do is we find the displacement s, and we can show the diagram where s is. That's the displacement s at a time of 0.95 seconds. So we go to our kinematics and we put down our kinematic rules. U, the initial vertical velocity, v, the final velocity at that particular time, a, the acceleration, uva, s, the displacement, which is s we're looking for, and the time t. Now the initial vertical velocity we worked out in the previous example is going to be 6.50 meters per second upwards. That's the initial vertical velocity. We don't know anything about the vertical velocity at time t, 0.95 seconds, so we can leave that. We do know the acceleration is minus 9.80 meters per second every second. The negative sign you must have, because in the rules of this game, everything is up the way is positive, everything's down the way is negative, and these are all vectors with the exception of time. The displacement is what we're after, and we do know the time is going to be 0.95 seconds. So in our equation list, we have got the initial vertical velocity, we have got the acceleration, we've got the displacement s, which we're looking for, and we've got the time. So we look up our relationship sheet and we have got this equation to deal with: s equals ut plus 1/2 at squared. So plug in the numbers. S equals u 6.50 multiplied by the time, which is going to be 0.95. Add on to that the second bracket 1/2 times minus 9.8, and then multiplied by the time squared, 0.95 all squared, and you can put that in a bracket. Now if you take your time and work out in the calculator, you get the displacement is going to be equal to 1.75 meters, and that's the displacement s. So this distance here is going to be 1.75 meters. So what's the total height above the ground? Well, we have to add in the 1.60 meters to get the true height above the ground. So the height above the ground, which we'll call capital H, has got to be equal to the height the ball was shown at, which is 1.60 meters, plus the height the ball rose to is displacement above the centre line, which worked out to be 1.75 meters. So that really is the true height of the ball above the ground, 1.60 plus 1.75. It's going to give us an answer of 3.35 meters. But the person has got a maximum reach of 2.10 meters. That leaves this little gap here then, h. So h must be the total height minus the height of the person. So small h, the height which the ball is above, is going to equal to 3.35 meters. That's the height of the ball above the ground. Take away the size, the height of the person, and the height of the person is going to be 1 point. If you look at the diagram, the height of the person will be 2.10 meters. So the height above the person who's reaching out to grasp the ball is 3.35. Take away 2.10 meters, and that's going to give us an answer of 1.25 meters. So the ball was 1.25 meters above the head of the player. Question 1 continued, part B. The Doppler ball is now threaded onto 2 ropes. There are handles at either end of the ropes, as we can see from the diagram. The circuit of the Doppler ball is switched on, and the loudspeaker produces a sound of frequency 622 Hz. Student A pulls the ropes apart, and the Doppler ball travels along the ropes towards student B. The ball travels horizontally along the ropes with a constant velocity of 8.60 meters per second. And for 3 marks, we have to calculate the frequency of the sound heard by student B as the Doppler ball approaches him. This is a kind of mixed question, this one, but we know from our relationship sheet we can work out the observed frequency, F0, is equal to the frequency of the sound, and multiplied by the speed of sound divided by the speed of sound plus or minus the speed of the source. Now for student B, we know that the velocity the ball is approaching him, and therefore we know that we're going to have to use then the minus sign for that. Think of the rule: if it's approaching you, minus, things are getting closer, minus sign. So F0 is going to be equal to Fs multiplied by speed of sound over V minus V, the speed of the source. So we just need to plug in our numbers. The frequency observed is going to equal to 622, that's the original source frequency, all over 340 divided by 340, and take away the velocity of the ball approaching, which is going to be 8.60. So just take your time, do everything slowly in your calculator, work it out, and you should get an answer of 638 Hz. And that's the frequency student B will hear as the Doppler ball approaches. Question 1, Part B continued. Part 2. The foam Doppler ball collides with the handles at the end of the ropes held by student B and comes to rest. Explain how the foam ball protects the circuit board during the collision. Well, we know that the ball is moving towards the person. It will have a momentum, and that momentum is going to be equal to mv. And that's your momentum before it comes to a rest. The momentum afterwards is going to be equal to 0 since it comes to a rest, and therefore we've got a change of momentum, delta p, and that's going to equal to the momentum after, take away the momentum before. That's going to equal to 0 minus mv. Therefore the change of momentum is going to equal to minus mv. Now, we know that we're looking at the size of this momentum first of all, so therefore the size of the change of momentum is going to be equal to mv. Now, that change of momentum is going to be equal to the impulse, so therefore we say that ft, the impulse, is equal to mv. Now remember, mv is constant because it's been travelling at a certain speed and it's come to rest, so that doesn't change. So we've got two options here. We can have the collision taking place over a very short time, which means the force, if we rearrange for the force, is going to be equal to mv divided by t. So if you have this collision over a very short time, you're going to have a big force, which can create damage to the circuit. But if you extend the time of the collision, extend the time where the momentum changed, then what you do is you increase the time t on the bottom here, and that means you're going to get a smaller force. So the whole idea behind this is that the foam which surrounds the circuit in the ball is designed, when it crashes into the opposite handles, is to compress. And when it compresses, it increases the time of the collision. It increases t, and that implies you're going to get a smaller force, a small f, which means in that particular case the small force will be a lot beneficial than a large force which could break the circuit board. So quite simply, it's the impulse equals the change of momentum. The change of momentum stays the same because it's travelling at a certain velocity, so you have to make sure that in this case the time of the contact is as long as possible to give the smallest force, which will protect any circuit or object in that ball.